Hello everybody, in this video we're going to be covering section 17.4, potential, free energy, and equilibrium. We're going to explain the relations between potential, free energy change, and equilibrium constants. We're going to perform calculations involving the relations between cell potentials, free energy changes, and equilibrium. And then we're going to learn about the Nernst equation. We're going to use it to determine cell potentials under non-standard conditions. So if we recall back to the last section that we covered, we learned that what was free about the Gibbs free energy is that is the maximum amount of energy available in order for us to do work. If we're talking about just redox reactions, all of that work is essentially electrical work. And a very smart man by the name of Faraday came up with an equation for the electrical work, which now allows us to relate delta G to our standard cell potentials here. So our standard delta G to our standard cell potentials. And that equation is negative NFE, where N is the number of moles transferred during the reaction. So we need to know what those half cell reactions are and pay attention to how many electrons were transferred during a redox reaction. Remember, it is often not just one. F is Faraday's constant, which is just a number that we need to know, 96,485 coulombs per mole. And E cell is the standard cell potential, which we know to be in volts or joules per coulombs, which is how these coulombs are going to cancel in this reaction, in this equation. Now, if we take that result and we combine it with our previously derived relationship between delta G and K, we can come up with an equation that relates K and E cell. All right, so we know that delta G is equal to negative RT ln K, and that it's equal to negative NFE E cell. If we take a look at just this part right here and then solve for E cell, we can see that E cell is equal to RT over NF times ln K. All right, this equation indicates that redox reactions with large positive standard cell potentials will proceed far towards the completion, meaning they're going to have high values of K. All right, and that meaning that the majority of the reactant has been converted to product. So we're going to have a reaction that lies far to the right when we have a large E cell positive. If we had a negative E cell, we would have a K value that is less than 1, and it's going to be shifted towards the left. I really like this graphic. I think that it's very useful because this is getting to be a bit complicated at this point. Basically, we can relate delta G, K, and E cell now. All right. So depending on which one you have and which one you want, you have the equation that you need to use here to be able to do that. So say I know K and I want to go to E cell. This is the equation that I'm going to go to there and be able to calculate E cell by plugging in K. All right. If I knew E cell and I wanted to go to K, I would need to plug in E cell and then solve for K in that case, right? And I could do something similar with delta G and K or delta G and E cell. You can kind of visualize what it is where you are at and what it is you want to know in this case. We had a table before relating K and delta G, and now we can kind of extend that to include E cell. Okay, so when K is greater than 1, that means that we're going to be favoring our products. Delta G is going to be negative, meaning that we're going to have a spontaneous reaction. E cell is going to be positive, meaning we have a spontaneous reaction. So we're going to be spontaneous under standard conditions, and we're going to favor the products at equilibrium. If K is less than 1, delta G is going to be positive, E cell is going to be negative. This means that our reaction is non-spontaneous under standard conditions, and reactants are going to be more abundant at equilibrium. Okay, we're going to have a reaction that lies to the left. If K equals 1, delta G is 0, E cell is 0, the reaction is at equilibrium under standard conditions, and reactants and products are going to be equally abundant. Now, just like we said before, most of our processes that we want to study are not going to be under standard state conditions. Okay, these are special conditions. So it would be really nice to be able to calculate the cell potential that we would expect under non-standard state conditions. And we saw that we could do that with delta G with this equation, right? I can start with the standard delta G for that reaction, and I can apply this fudge factor over here to get it at non-standard conditions. Now all I need to do is just substitute in my new expression for delta G, negative NFE E cell, and then I can do a little bit of algebra where I just am dividing by negative NF, and I wind up with this expression right here, which is called the Nernst equation, where I can first find the standard cell potential, and then I can apply a little fudge factor here in order to get the cell potential at any given time, or under any non-standard conditions. Now, we can actually rewrite that, and I did a little derivation of where this equation comes from. It's basically just combining together these various constants here, including having the temperature be 298 Kelvin, so standard temperature of 25 degrees C, and then doing a change of log here, because this is log base 10 versus the natural log back here. But if you do have a reaction that's happening at 298 K, this could be very useful, easier to calculate using that. And it uses the standard log base 10 that you see on pretty much all calculators. I mean, any scientific calculator is going to have a natural logarithm, but not, your typical calculator might not have that. I also derived another equation that you may want to look at in the homework, where it's simplified, but it still has that T value out there, so that you can actually use a simplified equation at different temperatures. So a concentration cell, real quick, this is kind of a different topic, but it leads into this. Now, because we now see that the cell potential is going to be different when we're under different concentration situations, we can see that we can actually have the same reaction happening at the two different cells. For instance, the reaction with zinc. But if we have the concentrations different, we're at non-standard states now, we'll still get voltage across that cell. Okay. So you can actually still get some voltage just by varying the concentrations of the two cells. And this is actually used industrially quite a bit in like power plants and stuff like that. They have designed a number of different kinds of concentration cells where they can basically run them backwards and charge them in order to store some large amounts of electricity, and then draw some electricity off of it so that they can have that electricity available when they need it.